And now I could show some list examples. So I will start with the one that I showed earlier. So you can create a list like this, which is just, again, just like creating a vector. So this one's called x of s, and then I'll create y of s, and I'll say this one's going to be 1 colon colon 2 colon colon nil. And then as I showed before, if I want to compare these two, then I would do that, and you see that they're true. So even though the syntax is different, they create the exact same list. And as I showed in the performance slide, when you use a list, you pretty much always want to prepend elements to it. It doesn't matter too much when you're using a small list, like 10 or 20 elements. I kind of use it just like a vector in that case. But when you're using much larger lists, you want to make sure that you are prepending elements. So you can create a list like this. So I could say I'll create a list of A is going to be a list of 3, and I can say val B equals, and this is how you prepend elements. So then you would prepend 2 to that one. And you can see that results in a list of 2 and 3. And then I can do val C equals 1 colon colon B, and then C will end up being this list of 1, 2, 3. So this is how we prepend elements. There's also a method, I believe. We do val D equals, so that I can say C dot prepended, and then you would do a 0 like that. So prepended is probably an alias for colon colon or vice versa, and that just means it's the exact same method. They just have two names. One other thing to note is if you want to prepend one list to another one, you do that with the colon 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 operator. So in this case, I'll just do like 8 and 9, and then you do colon 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 D, and that gets you that result. Another good thing to know about lists is if you're going to create an empty one, you need to give it a type right away. So instead of saying something like this, you can see that has this type of nothing, and that's not really what you want. So what you would do instead was you say val A colon, and let's say I want a list of int, for example, then you could do that just like that. Or the other way you could do that is to specify the nil element here. And nil is exactly the same as an empty list. So if I do nil equal equal empty list, then you'll see that that's true. But getting back to this example, what I'm trying to show here is if you want to create an empty list, you have to explicitly declare the type right there like that. And then you can begin prepending elements to it. So then you would say val B equals, oh, I don't know, 10A, like that. And then again, you just prepend elements just like I showed before. And since I've talked about head and tail elements, I want to show what that means. So what I'm going to do is I'm going to create a sum function. So we'll create a function named sum, and it's going to take a list of integers as its one input parameter. And because it's going to create a sum of that list, it's going to return an int as its result. And then I'm going to implement the body of the method using a match expression. And the way you do this is you start with the variable or the input parameter, which I called x of s. And you say x of s, and then I want to match, call match on that. And before I continue, I should say that this is going to be a recursive function. So it's going to be calling itself. And the way you work with a recursive function and a list data type looks like this. So usually I handle the nil case first. And what this means is that I'm looking at x of s right here, and I'm saying if x of s is the nil element, I want to do something. And so what you want to do in the sum case, and I'll just go ahead and do this, is you want to return 0. So when you get to the nil element, which again is the caboose in the list, is you just want to return 0. And that's because this is considered an identity element for the sum operation for a list of integers. And that just means that when you add 0 to a sum, it doesn't change the sum. Like if you had a number like 10 and you added 1 to it, then you're going to change that number. The result is going to be 11. But if you add 0 to 10, you just get back to 10. And that's exactly how this works here. And I'll show this more in just a few moments. So I typically handle that nil case, or again, the caboose first. And then what you do for all the other elements as you're going along is you break these down into head and tail elements. And you can see we're doing a little pattern matching right there. And then the way this works is you say on the right side over here, I'm going to say that I want to take the head element and then I want to add that to the sum of the tail elements. And so if you think about this last line, or actually both of these, we can have a list like val x of s equals, and let's do one, I'll do it this way, colon, colon, 2, colon, colon, 3, colon, colon, nil, right there. Okay, so again, nil is a caboose, and then each one of these you can think of as a console. So this is 1, it has a pointer to 2, which has a pointer to 3, which has a pointer to nil at the end. And then I'm going to take x of s, and I'm going to pass that into sum here. And you see that the sum is 6. And now a way we can see that this is working a little bit differently here is to add a little bit of debug code here. So then I will say, got the nil element for that one, and then I still need to return 0. And then this guy here, I want to bring that down, do that there. In this case, so again, I'm just operating on these two cases here, and I want to give us a little debug information. So here I'll say head equals $head, and then tail equals $tail. And then when I do a sum of x of s, you'll see that output. So this gives you more indication of how things work. So when I first call sum with x of s, so here's x of s up here, and it has these 1, 2, 3 elements followed by nil. So you see in the debug output, when I first call sum, it comes down to the head and tail case here, and it prints this line right here. And it prints that, okay, head is 1. So it got head out of the pattern match right here, and then it prints it here and said the head element is 1, and then the tail is the rest of the list, which is 2 and 3, and then the nil element is implied. Then it starts this operation. It says, well, I'm going to add the head, which is 1, to the sum of the rest of the tail. And again, the rest of the tail is right here. It's 2 and 3. So that calls sum again. So then we come back up here to the top. The list is passed in. And this time, the list is going to be 2 and 3. So it comes into the function. The match expression breaks that into the head is 2. And then the tail is a list of 3 right there. And then this value is going to be passed into sum right here. So here on this line, sum is called again. And it says, whoops, I'm still in the head and tail case here because I have a value of 3. And then the output shows the head is 3 right there. And now we get to a point where it says the tail is list of that, which again is the exact same thing as the nil element. So it comes to this line right here, and it says, okay, now I'm going to add 3 plus the sum of the tail. Well, now the tail is the nil element, or the empty list right there. So this time when sum is called, it gets that nil element, and then so it comes into this case right here. Then you get this output right here, the debug output that says you got the nil element. And this case returns 0 right here, and that ends the recursion. So now sum isn't being called anymore. So as long as we had a head and a tail right here, we kept calling sum. We were breaking the list down into the head and tail elements right here. Then we were starting to add the head plus the sum of all the tail elements. And that's what kept the recursion going, was these calls to sum right there. But now that list is matched right here, it just returns 0. And this is where all of the calls to sum end, and the recursion ends, and it returns 6 right there. And I want to add, if I didn't explain that very well right here, I explained it in great depth in at least one of my books, in Functional Programming Simplified. So if you have that book, you can look at it, and you'll see an example similar to this, and then I break it down with this debug output, and I break it down into more steps and smaller steps where I explain all that. But hopefully I explained that fairly well, and you can understand how this recursive sum operation worked. But the important part for this lesson is that this function sum takes in a list, and then as I showed in several examples so far, this is how a list is constructed. So then this code, all of this code right here, shows essentially how we deconstruct a list using a match expression, and we match on the nil type here, and then we match on the head and tail elements here. And to show just one more thing, if I haven't worn you out yet, let's do one more thing. I'm going to change this to a product, or yeah, I guess product would be better. I was going to say multiply. And what you want to do here when you're using a multiply function is you want to change that to a 1. And then I'm going to change that guy right there to product. And that should be all we need to do to create a product function. So this guy now is 1. And that's because if any number multiplied by 1 is the same number, right? So just like adding 0 to 10 gives you 10, multiplying 10 by 1 also gives you 10. And I'll discuss this more in this course. And I've discussed it a lot in my books, and I'll discuss it more in this course. But this one here is called identity element. So specifically, this 0 is the identity element for the sum operation when working with integers. And similarly, this one is the identity element for the product operation when working with integers. And the identity element just means that this value right here has no effect on that value when used with this operator. And this value, 1, has no effect on this value when used with this operator. And now I can show that the product function also works with x of s. And whoops, if you're smarter than me, you probably saw that there's a bug in the code, because I got this result when I did the product on x of s, and I realized there's a bug in the code right here. I have head plus the product of the tail, and it should have been instead head times the product of the tail. So the correct answer is not 7, the correct answer is 6. And the problem was that needed to be a multiplication instead of an addition. But other than the bug I had right here, you can see that the algorithms are very same. They're both implemented with a match expression, and in both cases I match on the nil element and then head and tail, and you just have to have the right algorithm here and the right identity element here. And just to drive this home one more time, I'm going to do the same thing for a list of string. So there's a string. I'm taking a list of string as input. It's going to return a string as output. And now before I type this, can you guess what the identity element is going to be when you're taking a list of strings and you want to do a sum operation on a list of strings? That is, you want to concatenate a list of strings. I'll give you a moment to think about that. And the answer is an empty string. And now in this case, I think everything else should be the same. So I do that. And now I can say sum. And here I'll just put the list in here. So I'll put a list of A, B, and C. So I'm passing now that list in, and you can see the familiar output. And then the summary right there is ABC. So this is really, you could call sum a concat or concatenate function now. So on a personal note, this whole concept of an identity element, like this one right here, is something I knew nothing at all about before I got into functional programming. And it turns out to be really cool. There's a whole bunch of math behind it, and I'll talk about that more when we get into the functional programming courses.